Okay, so this is the fourth day. So today we are going to take a little bit of detour, okay, and we are going to talk about something. For me, it's a very new topic. So even our group is working on this topic very recently. We call it the graphene electronic tongue. This is primarily to do with sensing, mostly chemi sensing, and we just published this paper in Nature. Okay, so you can see robust chemical analysis with graphene chemosensors and machine learning. So this is just not the hardware we were talking about so far. You remember we were trying to make the hardware for AI, right? We kind of had this argument about AI is so power consuming and we need low power devices. That's why we look into 2D materials and we are trying to make those devices. That is one aspect. But then the AI itself today is extremely powerful, right? So it will be foolish not to use AI to enhance the performance of our devices. And what I'm going to show you is that the AI can also enhance the performance of the devices that your hardware piece can give you, right? Because we're always looking for better sensitivity, better selectivity, a better sensor. Can AI enhance the performance of the sensor? Because that's what the AI is doing in all other spaces, right? It is simply taking the human expertise and kind of elevating it. Of course, this is not the actual tongue. We did not make this tongue. This is also AI generated. Okay, this was generated by AI. Okay, but our tongue looks like this. Okay. This is something a lot of you are familiar with. This is a PCB, right? A printed circuit board, and then we have all the connections. And this is where these graphene devices are, right? You see, these are as small as US quarter, even smaller than that. Right? It's a very small chip. And then we use this chip for primarily the application that we are going to look into is food safety. Okay. The reason for that is so we took a program, I will talk about that, this NSF ICOR program, where we identified that one question that we get often asked about, okay, you are making all these wonderful 2D material based neuromorphic devices, Centronic devices, but what is the killer application? Where are these devices going to be used in the commercial space, right? How do I commercialize these 2D material based technologies, right? And that's a question I think you will ask at a certain career stage of your life. Why am I doing what am I doing? I mean, how can I change really at a bigger mass scale life of people? And when we identify that food safety is something that we hardly care about, right? For example, this water that I am drinking, I do not know how much PFAS I have got in here. And PFAS are all these chemicals that has been left because of industrialization, right? Industrial byproducts goes into your water, and it can actually cause cancer eventually, right? Even for that matter, if you're drinking milk, you do not know whether the milk has been mixed with water. In India, so we know that milk is always mixed with water, right? I mean, in the morning when these goalas will come to give us the milk, we'll ask, "Kitna pani milaya bhaiya? Pehle ye bataiye." Huh? But you do not know how much water is mixed in the milk, right? And that could actually compromise the nutritional value of the food, right? And if you're giving it to a kid, then he will not have the proper development, right? And then he will have developmental related diseases, right? The same thing literally happens, and you see that today, although we have so many varieties of food, really there is not a sensor out there today which can tell me, right, which I can immediately check and tell, oh, this water is safe to drink, this milk is safe to drink, or this food does not have any toxic material that can actually give me diarrhea, right? And there is no the silicon technology has not solved this problem. So this space is wide open for innovation, right? And that's why we realize that this is food is something that everybody takes, right? Just think about the market size, right? I mean, the entire population of the world will benefit by having a food sensor, or for that matter, any chemi sensor that can even tell you about water quality. Arsenic, this is a big problem in India in different ponds and in village areas, right? Can you have a sensor which can tell you your water is arsenic free, right? So that's the overall bigger philosophy, right? That's where we are trying to kind of head. And we've spoke to a lot of companies like Walmart, Kroger, Coca-Cola, Hershey, Hershey makes chocolates, right? So we've spoke to a lot of companies, then say that we are really struggling because every time, and in the US there is a strong regulation. If you find, let's say for example, a toxic product in your food, the food has to be recalled, which means that if he has been distributed across all the Walmarts across the nation, they have to recall it back, okay? And that costs humongous amount of losses for these companies. So there is also a profit interest from the companies, because otherwise they will not work, right? I mean, only once they start losing money, they care about, technology, right? And because of these regulations, they lose, millions and millions of dollars every year, okay? So they just told me that if you can have a solution which is handheld, low cost, low power, right, and reusable, then we can actually solve a bigger problem, right? So this is the angle that we are coming in from to make this device work, okay? So now graphene is actually a wonderful material for food sensing. I mean, we have all seen the, the atomic structure of graphene, like it is the carbon atoms arranged in an hexagonal lattice. I think most of you have seen that. And yesterday I think we were talking about sp3 hybridization. Graphene is a material where the hybridization is sp2. So the pz orbital is actually unpopulated, and that gives you very good high conductivity of electrons in graphene. But you see that here all the carbon atoms are satisfied with their bonds, okay? It's a sp2 hybridization, right? And that is why there is no dangling bond. And this is the beauty of 2D materials, that there is no bond in the vertical direction, right? That's why they call van der Waals materials. And that is why they don't generally react with any chemicals, okay? So they are chemically absolutely inert. This is not true for most of the bulk material as well as other 2D materials. If you put one chemical versus the other, they will start reacting. But if you put acid, base, anything you throw it on graphene, it will not react, okay? So that makes it an universal kind of a platform to sense anything, because if my material that I am putting to sense starts reacting with my device, then it will not work, right? So graphene is an ideal material for chemi-sensing application, okay, because of the inert basal plane. Inert basal plane simply means that it does not react with any chemical, okay? Although it kind of go counterintuitive. Generally we do functionalization, we do surface activation. I will show you that is not needed because we use the power of AI, okay? So now let's dig deeper. So this is the chip, okay, and this chip has got a lot of these sensors. If I zoom in, there's a lot of these graphene sensors. As I keep zooming in, this is a single device where you have, this is the graphene channel. You can barely see it actually, okay? And then these are the source and drain contacts, okay? This is sitting on alumina like a transistor, right? It's a graphene transistor, right? But now instead of, it's a transistor where we are using graphene as a channel material. Generally it is not good, right, for a logic application, because graphene does not have a band gap, so it will not give you a large on-off ratio. It is not good for our general applications, but it might be good for chemi sensing, okay? So source drain, backgate, and then the graphene channel, and then we actually only expose the channel area to the chemical, and the rest we actually cap, so that the metal may actually react with the chemical you are putting on top. So we cap it so that the contacts do not react, okay? Graphene may be inert, but your contacts may not be inert, right? Because these are like gold, silver, or whatever tie, platinum that you are using, okay? So this is a device, and this is what happens, right? So this is, you remember this picture from our previous lecture: source, drain, graphene sitting on a substrate, and then graphene is very unique, and then we are capping it. This alumina is now act as a capping. Whenever you put a solution on top of graphene, you can use that as a gate dielectric. Earlier we had a separate dielectric which was an oxide. Why? Because if you put a liquid on top, there is always an electric double layer that forms at the interface of the graphene and the liquid, okay? And this interfacial layer forms because of any solution has got charged molecules, right? Most solutions will have charged molecules, and then they will organize themselves and create these dipoles, right? Now what does it look like? Does it not look like a capacitor, right? But how thin is the capacitor? This capacitor is as thin as this interfacial molecules, correct? So this is almost an EOT which is very small. The effective oxide thickness is very small, because this literally, although the liquid is like a drop, it's a big bulk material we are putting on top, it acts like an ultra thin material. You see? You have a question?
Yeah. So this, you are putting some droplet, right?
Correct.
Droplet size maybe some 2-3 microliter.
Correct. Correct. Correct.
And your device is nanometer region, right?
Correct.
So is it not that two devices will be giving response, or
All devices. So you put the,
given
I was showing this figure, remember this figure? You see there is a droplet over here, right? And this droplet covers all these transistors.
so that means I fix sensor
Everything is, yes.
this top electrode, I expect the principle I will use. So how
From the top, you just probe it from the top. You just, there is actually a wire over here that is connected back over there. You just probe it from the top. This one? Middle. Here. So this is the substrate. This could be anything. This could be literally anything. It could be SiO2, it could be alumina, it could be glass, right? It could be anything. It's a very easy device to make. You can actually make it. No, it doesn't have to be patterned. It doesn't have to be patterned. You can simply, transfer graphene using, the CVD. You can buy CVD grown graphene on copper foil, and then you can etch out the copper foil. You put PMMA on top, and then you put it on this substrate, and then just put two contacts. It's ready. Then you put the liquid droplet. The only thing that why we pattern it is we generally want to cap it with alumina, and then you want to open only the channel area. Otherwise, what will happen is, these liquids, because they have ions, there will be conduction through the liquid, right? Capping is important. If you really want to get good precise result, the capping part is important, because what the capping is not only preventing my liquid from reacting with this material, but you see there are a lot of ions, right? So now if I apply a voltage across these two, I can have current flow through this, but I could also have current flow through the liquid, because the liquid has ions and the ions will move. This is something I do not want, and that's why I put an insulator over here. Correct. That's why there could be no current flowing here. That's the idea of designing this device. So what happens is, if you look into these devices, this is all the device, and then all these source drain contacts comes out to the periphery. You see, this is where we actually wear bond the devices, and the droplet goes here. Yeah, contacts are outside. It doesn't have to be. It could be anything. It just has to be a metallic wire. Any metallic wire is fine. We are not doing electrochemistry, so it doesn't have to be an AgAgCl. Yeah, you can just do a normal wire. That's what we literally do. It's a little bit simpler, but when you come to this part, it might require fabrication. Okay, but this idea is clear that I can use a liquid as a gate dielectric, and the liquids are generally extremely good dielectric material, ionic liquids, which we generally do not use because of the fact, if I have an integrated circuit, I'm not going to have liquid flowing all over the circuits, right? That's why we do not use liquids, right? Because if you think about water, what is the dielectric constant of water? Anybody knows? Yeah, it's 81. And what is the dielectric constant of hafnia that we are talking about? 20. It was 20. Silicon dioxide is 4. So dielectric constant of water is 20 times higher than SiO2. So we should be using water gated transistors, right? It's just that we don't use it because we cannot control water in an integrated circuit, and there are other problems as well, right? But this chemisensing application benefits from this fact that any liquid will have a much higher dielectric constant and much better gate control, okay, because this is a different application space. So that's the first thing, okay, and that's why you see this is a quintessential graphene plot. Some of you may have seen it. I don't know whether all of you have seen it or not. So what you can do is now you can apply a gate bias, right? As you apply the gate bias, because there is this capacitor, the conductance of graphene changes, so does the current. Okay, so you see this is how a graphene based chemisensor would actually work. This part is clear, right? And now you see if you put different chemicals, right, the response is slightly different, right, because the composition at this interface of the liquid and solid is going to be different for different liquids. Not all liquids will have the same molecule. Based on what molecule is there at the interface, you get a fingerprint of that molecule in your device. Does that make sense? This part is clear, right? So this tells me that yes, I can probably use a graphene based device for chemisensing application, but that's just the beginning. Okay, I will tell you now the challenges of doing that. Okay, and there's a lot of papers out on this topic. Yes, correct. Absolutely, because every molecule, the dipolar strength will be different. Okay, and based on that, there could be a charge transfer between graphene and that molecule, and that leads to a shift in the threshold voltage. Not always. Yeah, not always. I will show you very soon that as I change the pH of the solution, what does pH do? It changes the concentration of hydrogen ions, right? And then it will change the Dirac point of graphene, because it is kind of doping, right? Because more hydrogen or more hydroxide groups you have, it will shift the characteristics one way or the other, right? This is like electron doping versus hole doping, right? So we'll see that. Okay, but this part is clear, right? That this is what is happening with my graphene devices. So I can use it as a chemisensor. Now this is actually very unique. I wanted to tell you that a lot of you are working on sensors, right? And generally, there are two things you will always do. You have a sensor, which is a channel, and then you put source drain contacts, right? And then you measure whenever you have the analyte if there is a change in the conductance or not, right? I think when first day you took a lab tour, you saw there was a response. The humidity sensor that ma'am's lab was showing you, that there was a response, and then once you remove that gas, it comes back, right? So generally you measure the change in the conductance, right, or the resistance or whatever it is, right? So this is how a typical chemi resistor works, because these are simple resistors, right, because they don't have a third terminal, correct? That is number one. And number two, you also learn that you have to either change the sensing material if you want to go from carbon monoxide sensing to nitric oxide sensing to humidity sensing, because this material has to be sensitive to what you are trying to sense, correct? Or you have to functionalize its surface, right? You have to put certain chemicals on the surface which will bind with carbon dioxide, right? Then it becomes a carbon dioxide sensor. Or if you put something which will bind with nitric oxide, then it will become a nitric oxide sensor. That is what we call functionalization. So many sensors require functionalization, right? And that's the problem, because once you have functionalized the surface for carbon dioxide sensing, you cannot use it for nitric oxide sensing, correct? So same sensor cannot be used for multiple purposes once you have functionalized, correct? And the other thing is you have only one information, which is the change in the conductance, right? Here you have an entire gamut of information for a given chemical. You see, for a given chemical, you are seeing a huge change in the entire characteristic because you have a third terminal, right? So that gives you more information. Here the information is only change in conductance, one parameter. Here I have a full IV curve corresponding to one chemical and the other chemical, correct? Remember, we are living in the era of data mining and AI, which is all driven by information, data. So more data I can collect about a particular chemical using the hardware piece, the better it will serve me to develop AI ML models, right? That's what I am going to come to. So this is what I have just summarized, what I just told you guys, right? Because here I can actually extract multiple parameters. Here you were extracting only the change in conductance. Here I can now look into the change in the Dirac point. I can look into the change in this on current, right? I can look into the change in the N branch current. I can look into the change in the on off ratio. So more parameters I can extract for the same chemical. Here it was only one parameter. What is the change in the conductance? Here there is more, right? This message is clear, that I can extract more information if I have a 3-terminal device versus a 2-terminal device. So therefore chemi transistors are much better compared to chemi resistors or just chemi sensors. Clear? Okay, this is kind of summarized over here. Now we'll take a little bit of detour and try to understand naturally what is the best food sensor or chemi sensor out there in nature. Any idea what is the best sensor? Huh? Now, catfish will come later, but tongue, right? But let us think about the tongue a little bit. We do not pay too much attention to our tongue, okay, but the tongue is a fascinating piece of engineering by mother nature. Okay. Tongue, how does it sense? Okay. Tongue has primarily got 5 different types of taste receptors. Okay. They can broadly categorize between sweet, sour, salty, bitter and umami. Umami is the taste of meat. Okay. I have taken it out because I am in Prayagraj. Okay. No meat here. Okay. So, umami test is not needed. Okay. So, 5 typical taste receptors. Okay. But then if you think very deeply, if I give you a rasgulla, right, versus a gulab jamun, will you be able to tell me which is rasgulla and which is gulab jamun? But why? Because both are sweet. Both are sweet. Our tongue can broadly categorize between sweet and bitter and salty. But how do you figure out difference between a rasgulla versus a motichur laddu versus based on your experience, of course, but then where is the experience stored? So, you are absolutely right that although our tongue can only specify broadly 5 categories, we can distinguish because we have a gustatory cortex. Make sense? Because whatever you taste goes into your brain and gets stored, that this is rasgulla, this is gulab jamun, this is motichur laddu, right? And then you think about also that people are wine testers, tea testers. Forget about gulab jamun and rasgulla, easy to figure it out. But if I give you just Darjeeling tea and Assam tea without telling you that this is an Assam tea, will you be able to tell me? Unless you are a tea tester, okay, who have trained their tongue to become really very good in differentiating fine differences, subtle differences between different chemicals. Same with the wine testers, right. So, not only that we can classify different tastes, we can also do very subtle differences between similar type of chemicals if we train it. So, training part becomes important. You see how the AI is coming, because AI is all about data and training, right. And then the third component is, think about the fact that the tongue has got these 5 different types of taste receptors, but there are many of each type, right. Let us say there are 5,000 of sweet taste receptors, 5,000 of bitter taste receptors, and that is why whenever you sense a chemical, each of these taste receptors sense it slightly differently, okay. And the differential sensing becomes very important, and I will tell you why. Okay. Because if you look into the different tongues in the nature, right, and ask, okay, so 5 type is very important, and this 5 type is present across the entire animal kingdom, right. So, now the question is whether a chicken's tongue is better than a human tongue, or if the human tongue is the most superior tongue, right. If you look into the chicken tongue, how do we differentiate between a chicken's tongue and human tongue? Because they also have got all these 5 taste receptors. Will a chicken be able to tell between a difference between a rasgulla and gulab jamun? They do not care, they just simply keep eating anything and everything, right. Do they have such an elaborate sense of taste? Probably not. Why not? Because the number of taste receptors is very limited. So, they have only 25. So, 5 of each kind. So, the differential response is very less. So, for them rasgulla and gulab jamun are the same. They cannot differentiate because there are only 5 which are kind of sensing these different types of things, right. If you go to dog or cat, little better, okay, there are 400 taste receptors. Dog has 2,000, right, human 10,000, okay, and who is the winner, because we have spoke about it, okay. It is a catfish, which is the most amazing tongue out there in nature, but can you tell me how many taste receptors are there? We human have got 10,000 of this tiny molecular receptors. How many taste receptors a catfish has got? 200,000, 2 lakhs, okay, because its entire body is tongue, okay. So, test receptors are distributed all across its body, and that is why the catfish can find very small differences in the chemical environment in an aquatic environment. Think about an aquatic environment, chemically chaotic, right? Everything is going on. Even in that environment, it can find a small secretion of blood from another catfish to identify that there is a predatory action going on. There might be a big fish which is eating another catfish and I should not go there, and can figure it out from a long distance, right? Which means in a complex chemical environment, because whenever you are making all these sensors, it is a controlled lab environment, right? A humidity sensor, if it has to work in a practical environment, there are so many other things, temperature, pressure, right? I mean all other gases, how are you going to measure it, right? It can do it even in that complex aquatic environment, right? Just because it has a lot of these test receptors, because it helps to take more information about the environment. Okay, this part is clear. So, two things are important. One, the tongue itself, the hardware piece, right, and the number, how many are there, or how much information I can gather using piece, right. So, amount of information and the hardware piece both work in conjunction along with your training process of the gustatory cortex, which gives you this amazing taste sensation, right. Without taste there will be no one, right. I mean khana is a very big part of our life, right. If we do not have at the end of the day good food, right, I mean some biryani is waiting for us, our motivation increases, no. So, see, I mean, and this is a marvel that mother nature has done, right, through evolution and whatever it is. Okay. So, now we are trying to derive the inspiration and create a very similar philosophy, and that is why I showed you that our hardware piece is very same, graphene device, because mother nature is not changing the hardware piece, the tongue is very much the same, the composition, but it is changing the number, and that we can do by putting a lot of graphene devices on the same chip, correct. So, we simply increase the number of the transistors. Yes. No, test receptors are the same, numbers are different. So, the hardware piece is the same. Okay. It is not that the eyes, eyes have evolved independently 8 times, okay. Tongue has evolved only once. Okay. So, so you can see that making an eye appears easier for nature, because they evolved independently. It is not like we have been following a same evolution trajectory and got to a complex eye. Eyes have been independently evolved 8 times. Okay. Tongue has not evolved independently. So, tongue is a continuous process, that is why it is a much more delicate organ. Okay, and we do not care about it, we are visual animals, because most of our information comes to our visual system, right. But most of the aquatic animals, that is where the life started, right. Life started without eyes, life started with tasting, chemical, and you can see the impact it does, right. That is why all the underwater animals have an amazing sense of taste or chemicals. Make sense? Coming to that, yeah, we are building on it. Okay. One more thing I will also ask you is quite amazing. So, generally when you make a device today, okay, and you measure something, you get a response. You take the same device and then measure the same thing tomorrow. Ideally, you would expect the same response, right, because it is the same device and same thing, but in reality that does not happen, because there is some variation from day to day. Let us say you make another sensor tomorrow, or let us say I mean you make one sensor and he makes another sensor, right. Whoever is good in making sensor will probably get a better response, right. It also depends upon your manufacturing variation. Although you making both are making a graphene device, who makes it also makes a difference. Although even if I have the same structure, ideally it should not be the case, right. I mean theoretically speaking, each sensor every time you make should be exactly the same, but that's an ideal world. We don't live in an ideal world, right? So there is variations, right? And that's why most of these nanomaterial based sensors are not deployed outside, because let's say today you measure pH 4, you got a response. Tomorrow you measure pH 5, you got the same response. So from the response, how will you tell whether it's pH 4 or pH 5, right? You see the problem, right? Because if your sensor response changes, you do not know the response changes because of the sensor or because the pH actually changed, correct? But now we go back to our tongue, okay? I don't think your tongues are the same, correct? But if I give you a rasgulla to both of you will tell me it's a rasgulla, right? But your tongues are definitely not exactly the same, because mother nature can never make two tongues exactly the same, right? So in spite of having variation from one tongue to the other, we don't have problem in classifying the test as long as we are trained on that. Of course, he has never tasted rasgulla, he will not know it. But if both of you have tasted rasgulla once, right, then you both will be able to tell me that it is rasgulla, right? You see, these philosophies exist in nature which we generally ignore. We are now going to go back and use that philosophy, which means that no two device has to be exactly alike to give me the final correct answer, right? This is generally not how we think from an engineering point of view, correct? We want to perfect everything and then go and find its application. And that's what I'm going to show you actually. This is what I told you, and this is where we are going to use the hardware piece which give me this data, and we are going to use the full wrath of machine learning, okay? Whatever is possible, deep learning, nearest neighbor approximation. I will show you how this, which mimics the gustatory cortex literally, along with the hardware piece which mimics the tongue, together works to give me amazing capabilities in my graphene chemi sensors, okay? So we'll start with a simple experiment. So we are trying to make a pH sensor, okay? pH sensor is important because pH changes so many things. In agricultural stuff, if the soil pH changes, it will really change what crop you can grow. It's true for the water that we drink, it should be neutral pH. If it's more acidic versus basic, it can create a lot of problem, right? Health problems. So, and you see that if you take a graphene device and measure the pH, because the concentration of hydrogen ion is changing, the Dirac point is changing, and there is also some other change in the characteristics. So what I could do is I could say, oh, now I have made a sensor, because for each pH I get a unique response, right? So I could use this Dirac point, which is this minimum current point, and plot it as a function of the pH value, different pH, and you can see that it is changing, right, this minimum current point, and they kind of follow a very nice line, correct? So next time if I put an unknown solution, and let's say I measure the Dirac point to be here, then I can say that, oh, this must be a pH of 7, right? If I measure the device and find the pH, the Dirac point to be 0.9, then I can say the pH is 5, correct? So I can say that, oh, I have been able to make a pH sensor using graphene, right? You write a paper, you publish it, you forget about it, okay? And then it just goes into the archive and stays there, right? And you never commercialize the technology. Why? Can you tell me why? Because if I measure it 5 times, every time the response is a little bit different. No? Correct? So now let's say, for example, if I measure, now I put an unknown solution and I say that my Dirac point is 0.9. From this, can you tell me what is the pH? Let's say I put an unknown solution, I want to know the pH, and I measure my Dirac point to be 0.9 volt. What is the pH? What is it? Because 0.9 could mean this, 0.9 could mean this. What is the pH? So I have lost my accuracy. I lost my accuracy, right? I can only say, oh, it should be between 5 to 6, right? I lost my accuracy. Why? Because the response changes every time for non-ideal reasons. It could be temperature, pressure, whatever you are measuring in summer versus winter. That's not all. if I take another graphene device and do the same, right? Now if I tell you my response is 0.8, what is the pH? What is the pH? Huh? 4 to 8. Is there any point of using that pH sensor anymore? Right? So you see, this is a practical limitation with deploying all the nanomaterial based sensors that you are making in your lab. Right? They are never commercialized. Right? And how to resolve it? You will go back to the lab, try to make sure that you do everything correct every time you make the exact same sensors, or you go to industrial power, because in lab setting you cannot ignore it, right? You are not making this in a industrial manufacturing plant where everything is well controlled, right? Where there you need to have billions and billions of dollars of investment to make exact chip every time, and this is why the semiconductor industry is so impeccably correct and it is so much expensive. Right? Setting up a semiconductor plant will probably take you hundreds of billions of dollars. Why? Because every time, every device has to work exactly the same. That's what Intel, TSMC, Samsung, these companies have done, right? But they did not have AI. Do we need to have exactly the same device? And the application space is different. We are doing computing, high performance computing. You need to make sure the devices are reliable. Here we are trying a completely different gamut of problem, right? Now the question is, can I mitigate this using AI, right? This is almost like different tongues, right? But tongue can probably tell you whether you are acidic or basic, right? In spite of two tongues being different, right? So now let's look into the power of machine learning. So the first thing that we are going to do is we are going to say that okay, here we are extracting this minimum point and plotting it as a function of pH. But is that the best figure of merit or the parameter to look into? We can also derive a lot of parameters. Don't worry about this, right? But as I was telling you, I could look into this current, and I could look into how this current changes as a function of pH, or this current, or how that changes as a function of pH. I could always take a forward sweep and a reverse sweep. This we always do, and we can look into the hysteresis window, because based on the charge at the interface, the hysteresis window will be different. As I was telling you that from this curve, we do not have to extract only one parameter, we can extract many parameters, right? That is the advantage of a chemi transistor, chemi resistor, right? So we can do a lot. These are just definitions, you do not even need to remember that. I just tell you that we can extract a lot of parameters, but all based on human knowledge, okay? Because what are we doing? We are taking the maximum versus minimum, maybe the slope of this curve at a given point, right? Whatever we can mathematically define, right? So we extract those parameters, okay? And then we say that okay, now instead of V Dirac, can I look into another parameter and see whether that has better stability or better selectivity? So we do that, okay? Lot of plots over here, but you see some of them may be a little bit better. You see this guy is a little bit better, right? I think I Dirac was the best somewhere here, yeah, I Dirac. But then this parameter, look at this, right, all over the place. So I can go ahead and then rank them, right, and say that okay, which is the best, which gives me the best accuracy, right? On basis of that, I could rank them, right? Who is the best student in the class, right? Who can accurately tell me, in spite of all this variation, right, what is the pH value? And you can see that the I Dirac is 1, the V Dirac that we are looking into is actually number 5, not the top candidate, right? So we can rank them. Clear, right? And then we could also say that okay, instead of looking into one parameter, can we look into two parameters at the same time, right? Because then, or three parameters at the same time, because three together may give me a better information, and that is something, but none of them can actually give me full accuracy, right? Remember that even if you have the top ranked student, he is still not getting 100 out of 100, right? I mean, the student might be getting 70 out of 100, but it's just that a poor batch of students, that this person is now rank holder number 1, right? So at least, I mean, what we will consider fully accurate is to that it is number 1 and also gives me 100% accuracy, and not a single one can give me 100% accuracy. That's what this plot tells me. But then if I use multiple things together, and this is something we call this nearest neighbor learning, this is an unsupervised learning technique. Okay, you don't need to know about that too much, but you see now, if I plot three things, since earlier I was just plotting one parameter, V Dirac, in a one-dimensional plot, right? We were plotting the pH in one axis and V Dirac in the other, and we were getting a line. Now I am plotting, three parameters, correct? And now you see each of them forms a cluster, correct? So each pH now forms a cluster in spite of having device to device or manufacturing variation, cycle to cycle variation. So whenever I put a solution, measure these three quantities, and it follows it falls in that cluster, right? I could say that it is this pH, right? Because now it is not a point, right? It is a three-dimensional space. So I have more information, right? So just from the information of V Dirac, I may not be able to say it is pH of 4, but combining the information of the V Dirac, the I Dirac, the maximum and minimum, then I can make a better judgment, right? It is all about, there is a murder that has happened. If you have one witness, you may not be able to trust, right? But if three people say that, oh, I have seen, then you will be trusting more, because you are getting reinforced, and these three people can be coming from different circumstances and giving you evidences. That's what investigation is all about. You want to collect more and more evidence that this crime was actually created. That's what this higher dimensional learning is, right? Instead of relying on only one information, you collect more information and then try to see whether I can make the judgment about whether it is pH 4 or pH 5, whether the person is guilty or not guilty. Kind of, you see the analogy, right? So this is the advantage of going to a higher dimensional space, which you could only do with a transistor, because you can get more figure of merit and not just one in a chemisensor, just the conductance change. Make sense? You see the power of information. Yeah? That's the main point. Okay. And then we show that, okay, even if you go to three-dimensional space, you can get to a certain accuracy, but if you go to even higher dimensional space, that instead of relying on three information, if you take 5 or 7 or 20, you get to almost 100% accuracy in spite of all this variation. Make sense? So that already shows you the power of information using chemitransistor. This part is clear so far? Any questions? Okay. Now we found that d equals to 5 is good enough. You don't even have to go to 20th dimension. I just cannot show those plots in a whiteboard. If it goes to 4th dimension, right? It could only show up to 3. So we are measuring, I think, 7 devices, each 25 times. So that is the amount of data we are gathering, and then we are, yeah. No, it is also. I will come to that actually. Once I finish, you will see a better picture of what we are doing at the hardware piece. But just wanted to make sure this philosophy is correct, okay, that we are deriving this feature. Now the next question is, so these parameters that we have derived, these all based on human knowledge, right? Whatever maximum, minimum, whatever we have learned, correct? But then one of the powerful aspect of artificial neural network is that they are very good in some features, because what we are extracting over here are features, right? Feature means minimum point, what is the maximum, these are all features of the characteristics, right? And we are deriving it based on our human knowledge. But we could actually give this entire task to a neural network. These neural networks are called convolution neural network. You see, this is a 1D convolution neural network, and they are specifically known for extracting features from a characteristic. This is something used for image processing. For example, if you go and stand in the airports nowadays, not in India actually, most of the airports outside the world, you don't have to have your boarding pass anymore, right? I just stand in front of a screen, it does a facial recognition, right? And you see, every time my face might be a little bit different based on, my hairstyle, what I am wearing, but yet it is able to tell whether it is me or some other person. Why? Because it is not looking into the full picture, but looking into some features of my face. Right? And each of us have different features, and that's what these neural networks are very good at, right? So convolution neural network, facial recognition is all done by this convolution network, and that is why they are very good in feature extraction. And so we asked that why are we ourselves extracting the features? Why don't we give the entire IV characteristics to the convolution neural network and let it extract whatever it wants, right? Whether it wants to look into the minimum point, maximum point, other things, let it do that. I will be completely hands off. So we take the data and put it into a convolution neural network, and you can now see I can do two things. I can extract my own features and then put it into a neural network for it to learn, because these neural networks learn to classify. So what I do is, first we take a lot of data, okay, and we train it that, oh, this data corresponds to pH 1, this data corresponds to pH 2. It's almost like teaching a kid, right? This is rasgulla, this is gulab jamun. So first we train it, okay. That is a training process that we do on this neural network, okay. And there are different algorithms. We generally use back propagation algorithm. That's a different entirely gamut. We are not going to cover in this lecture. So we train this network first. Then we don't use the entire data set. We only use 70% of the data for training and leave the rest 30. Then we test. It's almost like you first teach a course, and at the end of the course you give a test to the student whether the student have learned, right, based on the course material that has been taught. So now that's the process we call inference, okay. So then we put an arbitrary IV characteristics in the input and then see what the network tells me, okay. And let's say the network tells me it is pH 4. I already know that, but now I am testing. So I am the teacher. I am asking, I am giving you this data set. I have already trained it. The network is trained. Training phase is done, correct. After that, I am giving this data set to the network and asking, can you tell me what is this for? And the network tells me pH 4. Okay, then I check. So this is the predicted level. This is what the network tells me, and this is the actual level, which is the answer that I know. And you see, if the network is doing a good job, then all these diagonals should be 100, right. So if I give it a pH 4, it should be able to tell me that it is pH 4, right. So the predicted level should match with the true level, right. That should be these are called the confusion matrices. This is a typical term that we use in machine learning, okay. So ideally all of these should be 100, but you see there are sometimes sometimes it confuses 8 with 7, and we have kind of seen what is the background for that, because 8 and 7 have very similar kind of a response, right. It never confuses, you see, a 10 with an 8, right. It only confuses the nearest one, and which is understandable because we were extracting the features and giving it to them. So the overall accuracy was 92%, see, which is already pretty good, right. And here we are actually using the network and not that KNN thing. Remember, this is we are doing a different learning. But then when we did not extract those features and give the entire IV characteristics for this guy to learn, right, look at now the accuracy goes up to 98%, okay, which means that the network can extract better features maybe, right, compared to what we humans can do, right. This part is clear. Then we ask the question, and this is an unknown business in the machine learning community, that these are treated as black boxes. These deep neural networks are amazing, but nobody knows why are they so good. What is going on inside, even the best expert on artificial intelligence machine learning won't be able to tell you. They just know that it just works, okay. And this is again, this is a philosophical discussion, because when Jeffrey Hinton first came up with this artificial neural network model, everyone looked at him. He got the Nobel Prize this year, okay. He said, oh, this can never beat the human intelligence, okay. But look at where it is with this deep learning models today, right. So you don't know what this black box is doing, and this is evolutionarily very different. It is just networks of connection. The way the human brain works is completely different. The only analogy is at a very abstraction level, that okay, I have some neurons, I have some synapses, they are connected, that is it. But the way a neuron works is completely different compared to how this artificial neural network works, but yet it is more superior, it appears to be at least now, than in the entire humanity combined, right. So this is the power of the artificial intelligence today, just deep neural networks, okay, data and training, okay. Now The next question is, I told you we do not know why does it work so better. So this is for the first time, we try to get some interpretability to this neural network why. We tried to answer this question why, and that is probably one of the reasons this paper got accepted in Nature, because otherwise, people are using machine learning for everything, right? So this is the first we kind of use something. This is a lot going on over here. I will try to do my best to explain this thingy. So we use something called this shapely features. This is actually used in game theory quite a bit. So what you see is, so we are now plotting the graphene characteristics, but both the forward sweep and the reverse sweep. Okay, it's the same graphene characteristic that I was showing, but in a different representation format, forward, reverse, okay, for all of them. Now you see something quite spectacular. I want you guys to observe this figure for something. So let's first observe the pH4, okay, and these are from different devices, different tongues, response of different tongues to the same pH4, okay. Do you see something which is similar? The blue shade regions are the same, correct. Now let's look into another one. Let's say pH 6, okay. In pH 6 you see that this part is where it is kind of focusing on. Makes sense? Earlier we were only using the parameter VDRAC for everything, right? But the network is not looking into one point. It is first of all looking into a part of the characteristics to identify that is pH4. For pH4 it focuses on this part of the characteristics, which we cannot have any mathematical definition, because it is not Dirac point or maximum or minimum, right? There is no way for me to define a part of a characteristics, you see. But the network focuses on a part of the characteristics, and it focuses on different parts for different pH, right? It is not focusing on the same region. It is almost like it is focusing on different features, different people, to kind of identify whether it is this guy versus the other guy, right? If there is a Chinese person, they have smaller eyes, right? If it's an African person, they may have bigger ears, correct? So it is not always focusing on your eyes to characterize a Chinese versus an African versus an Indian. It's kind of that analogy. You see, that's what the convolution neural networks are good at. So even in a device characteristics, it is never focusing on just a conductance change. It may be focusing on the conductance change for one, but change in the maximum current for the other, minimum point for the other, but not even a point, it's a part of the characteristic. That makes it so much more powerful. Not only that, it also have these red regions, okay, which tells me, how does it tell me that this region is highlighted, means this is not any other pH, okay. So it is like an interclass and intra-class differentiation that this blue and the red region signify. This is too much to absorb, but I try to give you a little bit into what's really going on, okay. My students actually know even better than even what I am talking about, because this is all done by them. We just discuss, I understand, okay, but they are more experts than I am on this topic, okay. So, but you can get the idea of what these neural networks are kind of doing, right. They are not looking into these human derived features which we are restricted with our own knowledge, because we cannot define a part of the, how will you define this part? This is not even like equal importance. You see the gray, the shades tell me, if there is not shaded at all, no importance. It is highest blue means that the highest importance, right? But then there is like a increasing nature of importance to different parts of the characteristics, right? That's so much difficult for us to even comprehend, right? This is why the networks are so powerful. So blue colors are simply meaning that it uses blue to identify whether it is pH4, and red tells it that it is not pH5 or not pH6 and not pH7. Correct, correct. So if the eyes are big, it will tell that, okay, this is not a Chinese guy. Yes, yes, identify, okay, because we never do that. right? We never use the features to discard. The network actually uses two types, one to reinforce and other to say no, it is not. Both information are important for me, right? Correct. Yes. You not always reinforce. You always say, oh, this did not happen, so I can take this thing out. Yes.
It is also depend on the hidden layer, number of hidden layer also, because the more then there is a conversion.
The, no, so we are not looking into so input. We put input to the network. The network could be very deep, and then it gives an output, right? So we don't care about what is happening inside the network. We are saying that at the beginning, which part of the IV characteristics my network is focusing on. Once it has learned different pHs, okay. The depth of the network doesn't really matter over here, right? If I use a 7-layer network, 8-layer network, 10-layer network, the Shapley plots will come out exactly the same. Okay, this part clear? Okay, so this is a framework. Now with this framework, we will now delve into problems one by one, and as we proceed, the problems will become more difficult. Okay, we'll first try it. So pH, it works pretty well. Now the other thing I also like to mention is that now let's say for example you make a chip, right? You take a lot of data, train it, test it, and it works very well, right? That's what we have shown. What about you make a chip tomorrow, right, or the day after tomorrow? Do you need to again retrain it? You need to again take the data and again train it? Then you cannot have a technology or commercialization, right? Once you have trained it once, you should be able to make as many chips, you should be good, right? That is also possible. Okay, so when it learns this chip to chip manufacturing variation, right? So it takes a huge burden from us of making every device perfect, right? That's the power of artificial intelligence, right? You see, we train it on a different chip and test it on another one. We change it, and then we can do a random split. In every instance, the accuracy remains pretty high. Some outliers are there. I mean, that you cannot do because no tool is completely foolproof. Okay, but you can get to very high accuracy numbers, right? Okay, now let's look into more practical problems. So we go from pH to milk adulteration. Okay, why is it a more difficult problem? Because when I add a little bit of water to milk, the pH does not change. Okay, the pH remains the same. In fact, if you think about the chemical composition of the milk, it's literally the same. You're just mixing it with a little bit of water. You're diluting it, correct? So even if you have a functionalized sensors which can tell me whether it's a milk or not, can't really tell you whether it is adulterated or not. Isn't that true, right? So what we now do is no functionalization. Simply measure devices with different adulteration percentages, train it, and you see the accuracy of the network. Same sensor. Exactly. Same ID versus VG, no functionalization, and I get to very high accuracy. Now milk adulteration is generally not a classification problem, right? Because the person who is mixing milk will not come and tell you I have mixed 10% or 5%, right? It could be like any arbitrary percentage. So you should be able to do that, right? Measuring it, and you should be able to tell that whether it is 10% adulterated or 5% adulterated or 90% adulterated. That makes a big difference, right? Because if you adulterate it with 5%, that may not compromise the nutritional value, but if it's 50% adulterated, it is useless. Okay, so that is, so therefore when I train it, should I train it on 3.5%, 7.3%, 9.2%, 22.1%? It's an infinite space, right? So I cannot do a classification problem. What I have to do is a more continuous value problem. So here we use a very different neural network, okay, which is a regression neural network. Here I can also predict within 3% accuracy whether the milk is adulterated or not. So I could only tell you whether it is 5 to 8% adulterated or 8 to 11%. So I don't get to like a very precise number, but that actually is already good for many applications, right? So you also have to be application driven. You see, I mean, there are some scientific goals that, oh, I wanted to give a precision of 0.00001%. Maybe useless. Who cares if my milk is 7.9% adulterated versus 8.2% adulterated, right? So those problems again you can solve. 5%, no, 5% water, 10% water, 20% water, 30% water. Oh my God, this is wrong. Yes, not 95%. The other 95% milk. 95% milk. Yes, the other way around. Yes, you're right actually. Correct. You're right. Yes. This one is correct over here. Yeah. Okay. Do that. And you see here the chemical composition is very similar, right? But yet I can do it. And this is again the power of not looking into a particular point. But you see now for pH it was looking into different area of the curve. For milk adulteration it starts looking into a completely different area. Right? Now we go and do this thing for literally anything. Let's say for example different types of Coke. If I give you a caffeine free Coke versus zero sugar Coke, I don't think you guys can distinguish, right, if I don't level it, right. This is all kind of a mental process. Oh, I see the bottle, it is caffeine free Coke, I am drinking, I am not drinking something more very caffeine oriented or sugar free. But there is a lot of problem in the industry with adulteration, not adulteration, authentication, because somebody could just bottle it in the right bottle but can put a different product, right, and you don't know. You are तो आप तो अपने मन में सोच रहे हैं कि अच्छा कितना हाइजीनिक चीज हम पी रहे हैं, right? So we can also do that. We can figure out the difference between zero sugar versus caffeine free Coke just by training. You can do it for different types of coffee, right? A light roast versus a dark roast, and chemically they are all the same. Different types of milks even, right? 2% fat, fat free, almond milk, oat milk, so many varieties of milk are there, right? And yet we are not changing our tongue. So this tongue that we have made is far more superior than our tongue, isn't it true now? Right? This is not something possible with our tongue, but we can do it just because we can collect way more data than our tongue can do. Right? Question? Oh, okay, good. Good. Oh, no pH measurement. No pH. We are not measuring pH. You see, just put the liquid, measure the IV characteristics. We don't care what the pH is. The pH of all these things are same. So there is no pure versus adulterated. It is like, yeah, exactly. When we are training it, we are telling it in the training that this is Coke, this is zero sugar Coke. You have to go through the training process. If you do not go to the training process, not too much. So we actually use close to 7 to 10 devices, okay, and we measure every device 25 to 50 times, okay, and maybe take it from 2 different chips. That much data is enough for this thing to learn, because you see the response does not vary too much, right. So whatever it has to learn, it can learn with this much amount. If the data is too less, it doesn't learn. If the data is too much, then it overlearns, then it kind of messes things up. The amount of data has to be right. It's all like, I mean, if you learn, even if you think about yourself, right, I mean, if you learn something, too many things, then you also start to get a little bit confused. सब knowledge आ गए ना, तब उसमें भी problem हो सकता है. You got the kind of the philosophy, right, I mean, right. So you need to have the right amount of knowledge, I mean, but in this case it's a little bit different, not exactly the same philosophy, right. So therefore you do this training. So no pH, we are not measuring anything, we are simply measuring the IV. And we put this liquid, measure it, get the data, we change the liquid, measure it, get the data, and then we train the model, test it, and we find that it can do it, okay. And in instances you can get to pretty high accuracy numbers, you see. And again, I am showing all these Shapley plots just to highlight that again for different chemicals it looks into different part of the characteristic, right. Because every chemical at the end of the day has a very unique signature at that interface. Remember that molecular layer, even if I change that concentration, the signature changes. It's like your fingerprint. Every person has his unique fingerprint. Even if you are twins, your fingerprints are going to be different, right. So, that fingerprint which we human cannot distinguish by looking into the IV characteristics, the machine learning algorithm can, the neural networks can, right. That makes it more powerful. Okay, now the next harder level problem. Okay, so we are done with milk, adulterate, Coke. Okay, now we go to different juices. Okay, and we look into as they rots, as they become spoiled. Okay, why it is a different challenges. First of all, you have to know what makes an orange juice and what makes a pineapple juice, because the chemical composition of orange and pineapple juice are very different. If you want to make an orange juice sensor, you first need to know what is the chemical which is unique to orange juice, functionalize your transistor, and then go and kind of use it for orange juice sensing, right. The same for pineapple, grape, watermelon, right. And then as they age, it's even more challenging, because orange juice may age because of fungi activity, but pineapple juice may age because of oxidation of a chemical. So, when they age, you do not know whether I need to focus on oxidation of a particular chemical, or do I need to focus on fungi activity or the concentration of fungi in that particular juice. You see the challenge level 2, right? Right, the method you don't have no idea. So, first you need to know that, then only you can design a sensor which will tell you whether the orange juice is 3-day-old or 2-day-old, right. The same thing with pineapple and grape juice, isn't that true? But we do nothing of that, right. We just simply keep taking data for orange juice day 1, orange juice day 2, orange juice day 3, grape juice day 1. We collect a lot of data, information using that graphene characteristics. Use these graphene characteristics over days and stuff, literally all over the place, to human beings, right. Then we put it into a network. This network is actually a little bit more complex. I will not go into the complex nature of this network. Again, my students will be able to tell you more. But this network has a pipeline method. First, it's find out what juice it is, and then it tells you how old it is. Okay, so it learns that way, right. It's something also in our brain happens. We call it associative memory, right. As I was telling you, if I ask you, what did you eat 1 year ago today, you won't be able to tell. But if I tell you 1 year ago it was your birthday, you might be able to tell me, oh, I ate this thing. It's like an associative one, right. 1-year-old history, your birthday, right. The same thing, if I associate juice with the day, it might do a better job. So, that is like the organization of the network, and then it does wonders, almost nearly perfect accuracy. It can tell me what juice it is, and it can tell me how old it is. And it's also very important for health reasons, right. Right. Look at the accuracy number. Doesn't matter. So, you can also inbuild that. Correct. Yes, yes, very much. If you just keep an orange juice outside, you will see the way it rots is different. You will see, more all this fungi will kind of start growing. If you keep pineapple juice, it actually lasts much longer. Okay, it also depends upon how much is the real water content in that juice. Okay, for example, I never knew that before this course. Chocolate, right? You can keep chocolate forever; they never go bad. Chocolates never go bad. There is no expiry date on chocolates, because chocolate has no moisture, and moisture, anything that constant moisture, rots. Okay, chocolates has almost zero moisture, and you can keep it forever. After that, I have been starting eating chocolate. Doesn't matter whether it is 1 month old or 1 year or 2 year old. Okay, but you see, I mean, the take home message from this is, yeah, yeah, in principle, yes, right. The device structure is the same. The small 1 centimeter I was showing at the very beginning. I think next one. Oh, so what we are trying to do now is, so what we are doing is we are kind of connecting these to the printed circuit board that I was showing and getting all the results, and then using the machine learning model. I will have a slide. What is our ultimate goal? I will tell you how we are trying to integrate it and make it handheld. But I think at the end of the day, I also want to show you is that it is reusable. So you can use the same sensor, then wash it away, and then again put a different material on top. Right now liquid food. Right now mostly liquid food, but in principle a lot of people are actually interested working with us for solid, like spices, for example, are one of the most adulterated one. All the haldi that you eat, all the jeera and stuff, they are mostly adulterated. Okay, I mean, that was very interesting when we were talking to Walmart folks. They were saying, I mean, this Ukraine war is going on, right? And most of the sunflower oil comes from Ukraine. Okay, so ideally, if I go to the Walmart and if I look into the oil shelf, there should not be any sunflower oil, right? But it was full of sunflower oil, right? And even Walmart do not know where this sunflower oil is actually coming and whether it is actually sunflower oil or not. And there is no way for them to tell it, right? So this kind of sensors could be already very useful, for those applications. And then this is also very low power. Look at the amount of energy consumption, right? Only 100 nanowatt to a microwatt that we consume in order to do a single measurement. So if you are running it on a battery, it will run forever. The sensor will keep running forever. It's extremely low power, artificially intelligent smart chemi sensor, right? So you asked the question about the, yeah, I can show that first. Yeah, I will come to that. Yeah, time is very short. I will come to that. It is there towards the end. So we took this course, with some of my students because we were trying to really commercialize it. I mean, we still have the plan of commercializing it. So if some of you have a commercial mindset, want to open a startup, you should come and work with me as your PhD. It's just that it's very difficult to find because there's a lot of risk that you take. These are not just app making startups. These are deep tech startups, right? So this has more valuation. I mean, you can think about it doing it in India as well, because this is really not a rocket science what I showed you today, right? It is literally combining very simple devices with machine learning, and then you can get to this thingy. So we spoke to a lot of companies, Welch, all these grape juices that you get, they are from Welch. They have this problem of patchouli, right? If there is patchouli in grape juice, they have to recall all the grape juices, right? That's millions of dollars. And our device can actually sense patchouli down to a ppm level. And that's good enough. You don't have to go to ppb because that's not the requirement. If it's a ppb level, it's not a health hazard. So you don't need to design a sensor, because there is always this idea that, oh, what is the lowest level of a chemical that I can detect with a sensor, right? Not needed. I mean, look at a practical application. This is what we learned in the iCore. This is a wonderful program, that the US government actually does. So this is run by the National Science Foundation. Okay, and they just give you, $50,000 just to go and do something called customer discovery. Because generally for us, we are working in the lab. Our approach is, let's first make the perfect device. Once the device is perfect, I will go and find out where it can be used. Okay, I will talk to potential applications. That's the absolutely wrong approach. First, you go to the market and find out what challenges are there, and then see whether you can solve it, right? For example, if I were to make a patchouli sensor and working in a lab, I will try to make a sensor which works at a ppb level, right? I will try to optimize my device and try to make sure that, oh, it has the best sensitivity, I can get a very high impact paper. But does anybody care about it? No. This problem is actually much easier because you are only trying to detect what? Even 10 ppm. Good, that's the federal regulation, right? As long as I can detect 10 ppm, you're good. And your sensor that exists today may already do that. So that is already kind of market ready, right, for this problem. Make sense? You see? So this attitude got changed once we took this iCore program, right? It's an amazing program. This is a intense program in 6 weeks. It's a 6 weeks program, okay? In this 6 weeks, you have to go and talk to 100 different customers in just 6 weeks. Okay, it's not easy. You have to email them. Most of people may not reply, as you don't get reply when you email us, right? So it's a very intense program, but it's a very enriching program actually. And this is the good part about the US. They have an ecosystem. where they really want to kind of bring the best technology outside academia and then accelerate towards, deep tech startup. That's why we have, Google, Facebook, Meta, all these companies exist in the US. Today US has the top 10, all the top 10 technological companies today are all from US, right? Even like 20 years back, there were other companies, let's say from Japan, Korea. Today, no. All top 10 tech companies are from the US. Okay, I hope the Trump administration does the same. Not going to say much about it. Okay, then the PFAS. Okay, PFAS problem is actually more difficult because the PFAS regulation is that here you have to go to even parts per trillion. Okay, that is so small quantity can even create health hazards. And today there is no technology that can do PPT level, parts per trillion level. We have been able to go down to, I think, parts per billion, okay, which is good, but we have to still improve this technology to go to parts per trillion. And there are, so PFAS are these industrial byproduct small organic compounds, okay, that came out during the industrial revolution. And most of the companies, this byproduct and the waste that comes out has these very small organic molecules. And there are many, there are like millions of PFAS which has been listed, and these are a huge health hazard. Okay, I mean, yes, to some extent, yes, to some extent, yeah, very similar. Okay, and this cannot be destroyed. The problem is that these cannot be destroyed. Okay, so they are going to stay there. So you have to somehow eliminate these things, right, and then collect it and then kind of do some waste management of that. So most of the waste water treatment plants, we spoke to a lot of them, this is a severe problem. A lot of industries are going towards using chemicals which will not produce PFAS. Okay, that's a big drive. I do not know about India whether there is any concern about PFAS here, but this is a big thing that is in the US, and Europe is even more stringent. Okay, because Europe is always ahead in terms of health and hygiene. US always lacks a little bit on that. I do not know what the new administration will do, but I mean this is a serious problem. Okay, if not for our generations, at least our old ages, and for the next generations to come, right? So it all up upon us, what kind of an earth we want to leave for the next generation. So this is a big problem. So we are also looking into that. This was a very interesting thingy, Tyson. This is a company which makes meat. Almost 60% of US meat comes from this company. We spoke to them, and they make fried chicken. Okay, and their problem is very unique. You talk to these customers, you understand their problems are absolutely unique. But so they told me that, can your sensor tell me the oil that I am using for cooking, frying my chicken, can be used for 5 times or 6 times, right? Because if I can fry the chicken in the oil without degrading the quality of the chicken in the oil for 6 times, I save $10 million. See the problem? We won't even imagine that that could be saving a company tens of millions of dollars just by knowing whether the oil can be used 5 times or 6 times. But it makes sense, right? Because they are making so much of fried chicken, it counts. Every drop of oil for them counts, right? So we were able to kind of, we are now working with them. Hershey's chocolate. These chocolates actually have a lot of these allergens. Okay, I mean in India we don't have this problem of allergy too much, but in the US a lot of people are allergic to nuts. Let's say for example milk, egg, and a lot of chocolate products have these things. So they wanted to know whether there are like known allergens in this chocolate, right? Very different problem. We never try to build a sensor for detecting allergens in chocolate, right? So we are currently having a project with them, Hershey. The good part is the students like this project. Free chocolates, right? Not for me. I will probably get a sugar, if I keep having this much of chocolate, right? A lot of wine companies are interested, That I am very interested, because these are French companies, French wine. If I can get them, I will say that okay, I will do the research for you for free. You just send me free wine bottles, the best French wine, and I am happy, right? So yeah, a lot of problems, and this is our ultimate goal. This is what you were asking. Right. So what we want to do is, so this is the hardware piece, right? We wanted to, it's almost very minuscule right now, and then we want to train the machine learning model and then create an app. So this app part is important. because now what will happen is, if I build a wireless module with this sensor will sense wherever it is and wirelessly communicate it with the device, right. And in the device will be connected to the cloud where my models are stored to identify whether the milk is adulterated, the coke is adulterated or not. So this is the ultimate solution, right, combining a handle, kind of a cell phone kind of a thing with this device, which could be placed literally ubiquitously anywhere, right. This we have not done yet. So to the it can go to cloud, and if the model is not too big, you can store it in the phone, right. It all depends upon how big is your model, right. If the model is small, it can be stored in the app, and if the model is too big, and then we will need internet connectivity, right. So this is a startup that we are currently working on actually, and this is all about this research, and you can also do it inline. A lot of companies have this problem of monitoring chemical processes inline. So you can also inbuild that if you build microfluidics with our devices. So this is something that we have still not started, but if some of you are kind of very good at microfluidics, please contact me. I will definitely have opening on that, where we are trying to integrate microfluidics, because then fluids can flow. Then we can also do for for glucose monitoring, for blood monitoring, anything. But that has to have a lot more there's a lot more nuisance attached to doing things in the medical space because of regulations, right. I mean, it has to be biohazard free and things like that. Yeah, exactly. So that kind of concludes, right. This is what is all about the graphene tongue. Okay. So any questions I will be happy to take. You can read this paper, okay, and yeah, this is in Nature. It should be, you should have access to the Nature journal, so you should be able to get this paper. Yeah, and any model, if you are interested in collaboration, I have a lot of students who are working on this machine learning part right now. It is not restricted to only chemical. Right now we are also trying to make an electronic nose, so that is for gases, VOCs. So yeah, any questions that I will be happy to take now. So this is probably the first part. T is there, okay, very good. Solid we will do, but it will take some time, because I mean, this solid, if I put it on graphene, it's not a solid interface, has no property like that. It has some importance. Okay, so graphene is probably your best friend in this matter because of two things. One is, as I told you, the inert basal plane, and graphene does not react with anything. If it is MOS2 or WSC2, it may start reacting, and it may not be an universal one. Yeah, I mean, it is just that the sp2 hybridization is extremely stable, extremely stable. It is not true for any sp3 hybridization. And when you have MOS2 and stuff, right, it can still react. Okay. So no other material has like this pi electron cover? Very less. I mean, some of these topological insulators do, but only at the surface, right. So yeah, very difficult to get this pi electrons. Yeah, that makes graphene very unique. Yes. Yeah, that's why I'm saying, I mean, this is what we learned actually. Yes, that your simple device could solve a lot of problems. No, 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 no. No, yeah, that's why I think Nature really liked it, because they want something which is very simple but very very effective for a wide range of audience, right? You have a question? Yes. Huh? That yeah. That's why I'm saying that we are also trying to make a e-nose. So you're not talking about the nose, right? So we're talking about the tongue. You can do both as well. You can do, yeah, I think maybe today we'll talk about multisensory integration. You will see the importance of multisensory integration, because when we make a decision, even about the food, it is never about just the taste. It is also about the texture, right? And when you have a laddu versus a rasgulla, the texture is different. That also tells you that. So texture is touch. At the same time, the smell, when you have I mean, a biryani versus a fried rice, the smell also gives you additional information. So multisensory integration is something that we'll cover today in the following lectures. But yeah, you can start combining all of these things together. Nothing prevents you from doing that. Huh? Huh? It will change. The result will change as long as, so you should not change the So we'll now look into some of these, animal-inspired computing. This was the very first work that we did out of our group, which is inspired by barn owl for sound localization. This was a very old paper. I think we published it in 2019, so almost 6 years now. So sound localization. Okay, so sound localization is generally a very difficult task, and the barn owl has literally mastered it. And you can see that it can localize sound with a precision of 1 to 3 degrees. Okay, because it does not use its eyes to find the predators at the place, because it hunts in complete darkness. So it relies on the way to find out which direction the sound is coming from, and it could precisely go and feed on rat or whatever animal it wants to feed on. Now, sound localization. I don't know whether you guys have heard. I mean, before this, discovering this barn owl's interesting circuit, I never asked, why do we have 2 ears, right? Because we could have only 1 ear for hearing, right? Sometimes we say that, okay, it might be because of balancing, right? But evolution could have chosen to give us only 1 ear, because there is only one nose, there is only one tongue, right? So what's the advantage of having 2 ears, and that too on the 2 sides of the brain? Okay, one of the advantage is that it allows us to do sound localization. Okay, why? Because whenever the sound comes from in any direction, you see that it reaches the 2 ears with a very small time gap, right? Because if the sound comes from the right side, it will reach my right ear first, and then it will reach my left ear, right? There is a very tiny time gap in that sound reaching your left and the right ear, and this is what we call this interoral oral time delay, this ITD. Okay, and it depends upon the head size, right? If you have a big head, right, then you can see that the time difference could be of the order of a millisecond, right? Because sound has a finite velocity, and if you have a small head, then the difference is going to be small, right? Because the time difference going from this ear to this ear is not going to be long. Make sense, right? So based on whether you are an elephant or a barn owl, this time difference ranges from hundreds of microseconds to a millisecond. Good? But there's a problem. The problem is the neurons in your brain can fire only once in every few milliseconds. You see, so you are trying to solve a computational problem that lives in microsecond space using tools which operate in milliseconds. It's almost like you are trying to use an optical microscope to see an atom, right? So you can only see the length scale, right, that is viable by the optical microscope. In this scale is the time. Neurons don't allow you to recognize anything, because before the neuron fires, the sound has reached both ears, right? See, sound localization is a difficult problem, because you cannot go backwards in evolution and change the firing time of a neuron. Right? So how do you solve it? So how do you solve this, this temporal problem? So firing means that the neuron, if an information comes, to the time it takes to fire, the minimum one is a millisecond. And between 2 firing, it's like a millisecond gap. So therefore, between 2 firing, if the information comes and goes, you don't know that there is an information that actually came, right? It's almost like you're looking with optical microscope into something that cannot be seen using optical microscope, correct? That's a problem. So how the barn owl has done it is using a special neural architecture that transforms the temporal coding, the temporal information, into a spatial code. Okay? And this is what it is. This is called a Jeffress model. So if you look into the barn owl's brain, you will find this organization of these neurons. Okay? It uses 2 types of neurons. One are these red neurons over here, right? These are called coincidence neurons. What does the coincidence mean? If the information comes at the same time, they fire. That's coincidence, right? So every time the neuron receives information from the top and bottom neuron at the same time, this will fire. But if it receives the information now and later from this guy, it will not fire, right? So that is what a coincidence neuron means. And then it has these delay neurons. You see these lines? These are called delay neurons. So what do? They convert the sound information, acoustic wave, into electrical spikes, right? Because that's how the brain works. Brain only knows electrical signals, and brings it to these neurons. And there is one on the right side and one on the left side, this delay neurons. This is the architecture. Now the question is, how does this architecture solve this problem, right? So now let's look into this. So let's say the sound is coming from straight ahead over here. It will reach both ears at the same time, right? So the velocity of propagation in both the bottom and delay is the same. So therefore, where the coincidence will take place? At the middle, right? But if the sound comes, let's say from the right side, it will reach right ear first. There will be longer propagation here and lesser there, so coincidence will take place at the left side. So you see, so depending upon which ear it came, the coincidence takes place at a different location. Did you see that, or do I want to replay it? So straight ahead, it reaches both ears at the same time. Coincidence happens at the middle. If it comes from the right side, reaches right ear first, longer propagation in the below one, and shorter in the bottom, and the coincidence happens in the left. Make sense? So now, by knowing where did the coincidence took place, the Barnard can tell which direction the sound came from. Make sense? So it has converted a temporal information into a spatial map. Right? Isn't that amazing? This is how nature works. You know, look at the engineering of nature, right? If I cannot solve something using the tools that I have, let's design and engineer something which can work at that time scale. Make sense? So here I'm not limited by the time anymore. Got it, right? So this is something we want to now mimic in our devices. Okay. So how do we do that? Do I have this thing? Yeah. Okay. So this is what is the device. Okay. First, let's look into in the broader perspective. So here you see these lines. These are delay lines. Very similar. And if you zoom into this device looks like a transistor with source and drain, right? And then you see these lines over here. There's a channel over here which you can't kind of see. It's like our MOS2, hardly visible under ACM. Okay, you see that there are these electrodes, and the spacing between the electrodes are changing, varying, right? So how does this device kind of mimics this is what we are going to see in the next few slides. Okay. Now we'll dig a little bit deeper into transistors. Okay. So this is a single device. Let's look into, we call this split gate. So generally a transistor has a single gate, right? A top gate which is continuous. Now I have actually broken it and splitted it into two. Correct? So this is a single, so forget about these, just look into a single one. A single one looks like this, right? I have a source, I have a drain, and there's a channel, and then there's a gate which is not continuous but has a split. This part is clear? So now let's look into this device. So it is a fully top gated device which we have been studying so far, right? It has two states, right? If the input VTG is low, then the output is high, right? And if the input is kind of minus 30, then the output is low. Clear? That's a transistor switch, right? It's a switch. It goes between high state and on state. Now, how does a split gate transistor work? Right? So now, if I have two gates, you see that when only one of the split gate I am, operating it with, I cannot turn off the transistor because I am not applying any voltage over here. So if it was on, it will remain on because one side of the channel is not gated. You got that, right? So I cannot turn it off. I cannot turn it off either by using this gate or the other gate, if I'm only using those. I can only turn it off, right? So therefore, if I look into the inputs, you see that when both gates are 0, of course it is high, I'm not applying anything. If one gate is, I'm not applying anything, in the other gate I'm applying, I only get to this state, right, which is also high. If I apply minus 30 to one gate and 0 to the other, it's also high. But if I apply potential to both the gates, then I can turn the transistor off. Is this part clear? Right? So if I do this, then it is low. Correct? Now this transistor is almost like a coincidence detector. Isn't that true? Because only when I have gate voltage applied to this and this at the same time, I can turn the transistor off. This part is clear? So I have been able to create a coincidence detector using this split gated transistor. Right? That's the first part. Right? The next part is the spatial map. Remember, I have to have multiple of these things. So now there's another interesting thing that is going on. You see that this transistor, when it's fully gated, it goes down to complete off state. Correct? But now when there's a gap between them, I do not go down to this level of current. You see, I could only go down to 10 to the power minus 10. Why? Why is that? Because the part which is ungated, right, will still conduct, right? But if it still fully conduct, then I should still get a very high current, right? Because I should not be getting, 3 orders of magnitude smaller current, because the gap is not, 3 orders of magnitude smaller than the entire transistor, right? The gap is as big. If you go back to the previous slide, you see this gap compared to this is maybe 1/10. So the current should only go down by 1/10, 9/10, right? Because this gap should still conduct. Agreed? But I can still have some control over this region. Why? Because of fringing electric field. Because the electric field not only goes straight down, but if you remember this capacitor structure from your old textbooks, you can say, no worries. Just check. If you have a parallel plate capacitor, right, there are electric fields. Won't there electric fields like this? These are called fringing electric fields. Correct? So this fringing electric field has some control. From this electrode controls this part, and this electrode also controls this part. Make sense? And therefore you have some control, not as good as the top gated device, but some control that gives you, this lower current. Clear? Now you tell me this current is going to be higher or lower if the gap between the electrode is more or less. So I will draw you 2 pictures. Right? So there is this transistor, source drain. In one instance, I have this. This is, let's say, number 1, and number 2. Let me move this. Okay, and then the other one has a smaller gap. Let's say this is 2. Okay, which one do you think will give me, over this current? Second one. Why? Because the gap is smaller, so therefore the fringing fields will have more control over here, because the fringing field can only go up to a certain distance, right? They cannot control this area if the gap is very large, right? So by creating different gaps, right, let me see, right? So this is clear, right? This is a coincidence neuron. So only when the voltage spike comes at the same time, I see a dip in the current. This part is clear, right? For a given gap. You see, when both of them are together, both of them are minus 30, the current goes down to 10 to the power minus 10. Okay? This is coincident detector. And this is what I was talking about. You see, this is the COMSOL simulation showing the fringing electric field. The electric field is highest, marked by red, and it kind of gradually diminishes in this gap. But still, it is not all blue. You see, there is a finite yellow color, which means that I have this fringing electric field in the gap. Right? And this is saying this COMSOL multiphysics simulation, which shows that although it is minus 30 volt at the electrodes, in the gap, the electric field is not minus 30, because of course it is far, it is around minus 20. This part is clear, right? And then as you make the gap bigger and bigger, you see that instead of minus 20, if the gap is large, the voltage is even smaller because the effect is lower, right? So if there were no gap, right, what will be the voltage here? 30, minus 30, right? Because that's what I am applying here and here. If there is some gap, if this is minus 30, this will be smaller than that, right? Minus 20. Now, if the gap becomes even larger, you tell me what will be the voltage at this middle point. Close to 0, right? Or maybe like minus 10. If it is even further, that's what is happening. You see, for the smallest gap, you see the voltage is minus 20. For the largest gap, the voltage is minus 10. Makes sense? Correct? So if the voltage across the channel is different, then your off currents are also going to be different. And you see, when your gap is the largest, you can hardly get to this state. If the gap is the smallest, I can kind of turn it off. Make sense? So far so good, right? This part is fully clear. So what I am doing here is literally fringing field engineering, right? Just by changing the gap. Now, okay, this is the flake. Now it's visible actually. The flake was actually, this was on exfoliated flakes way back in 2019. Now you see, if let's say for example, I apply a voltage here, minus 30, and apply a voltage here, will I be able to completely turn this channel off? No, right? Because they are occurring at different locations. I could only do it if it vertically happens at the same location. Correct? This part is clear, right? So I kind of create this ratio, inhibition ratio, and then I plot the ratio of the current as a function of, if the voltages are applied at the same top electrode and bottom electrode or different top electrode and bottom electrode. So 200, 200 means that I am applying VSG of minus 30 to both the blue ones. Okay? And this 200, 600 will mean that I am applying minus 30 here and minus 30 here, right? So the diagonal elements tell me that only when I apply it on the top and bottom electrode at the same time, I get the maximum effect, right? Because this ratio between the high state and low state, right, kind of keeps, kind of highest in the diagonals, and it is high, the maximum for the smallest gap. This part is so far so good, right? So now if I were to plot this, you will see that the current dips only when they match in time domain, right? Only when the two yellows coincide, I get a dip. But then look at the magnitude of the dip, different, correct? Magnitude of the dip is different, and this is the philosophy behind why the dip decreases. So now, if let's say the sound comes from a different direction and some coincidence happens, I am just measuring the source to drain current. Just by knowing whether there is a dip, I will know that sound is coming from some direction. And by knowing what is the magnitude of the dip, I can tell which direction the sound is coming from, because that will determine where did the coincidence took place. Make sense? Right? So this is literally mimicking that neural architecture in the Barnard spectrum. Correct? So that's what we are doing. And if we do that, and then we design all the RC delay neurons, these are simple things, right? I mean, delay neurons are nothing but RC circuits. R and C creates delays, right? So you can create all these delays, right? Because you have to bring the sound information from the two sides. So that's what we all do. And then eventually, one more important thing that I did not mention is the, so that is clear, right? That how we are mimicking the Barnard's brain. Now, if you think about this device is also have a global backgate, okay? Which means that I can turn this transistor off completely by backgate, because the backgate is everywhere. The top gates are splitted, but there is a backgate all over the channel from the back, okay? That I could use for adaptability, because let's say for example the Barnard is in the sleeping mode, right? Then does it care which direction the sound is coming from? No. When we are sleeping, do we care if there is a sound or not? Correct? So your neurons should not even fire when you are sleeping. Or let's say, for example, it is not very hungry. Then even then a sound signal is there, do you care? Right? Because every time you care, you will become too much aware and you will start taking actions, and that will be costing you energy and resources. So that adaptability can be given because the same characteristics for a 200 nanometer channel length, this gap could be controlled by applying different backgate voltage. Okay, which means that I could make the backgate completely. You see, at 200 nanometer, we want a large difference between the on and off, right? But by applying some gate bias, I could also make it almost non-responsive to whatever is happening in the top. You see that? If I make the backgate voltage change, then nothing will happen with the top gate. I am disabling the top gate by using this backgate, right? Or I could actually see my ratio earlier over here. If I go back, what was the ratio? Very small, right? For this 200 nanometer, it is going from 10 to the power minus 6 to 10 to the power minus 8. This ratio is 2 orders of magnitude. I could also use a backgate right here now to increase the ratio much higher, right? Much higher means my sensitivity has now increased. So by changing the backgate, I now control, how well my neurons respond. They may not at all respond, and they may respond, very, strongly, right? So that's what we kind of show that. Sorry. So we are looking into the coincidence part. Yes, exactly. So we are looking into coincidence situation, but under different backgate condition. Make sense? And you see that this diagonal that I was talking about, right? This is the best diagonal I want to have, where this number is as high as possible, and that happens when I apply a positive backgate. But if I apply a very large positive backgate, you see they're all the same. It doesn't matter whether the coincidence happens or not. So that's almost very similar to, the barn owl is sleeping or restful. It is not very hungry. And this is, it really needs to find food. Right? So this adaptability can also be used by just doing a device engineering and using both the top and bottom. And if you do that, now you see the precision of this device. So barn owl can give you a precision of what I told you, 1 to 3 degrees. Look at what the precision of this device could be. Fraction of a degree. Right? Fraction of a degree of precision we can get. And then there's a lot of other things. We should not go into all the details over here. This is a very involved curve. If you go and read the paper, you will have a better understanding of all the details. Okay. So this is kind of something that we talk about. We don't need to go through all the details of this writing, but you got the gist, right? I mean, we are literally using a very specific device, a split gated transistor, and doing this fringing field engineering in this case by having different nano gaps to model the brain of the barn owl for sound localization. Good? Yes. Correct. You tell me where could be the application. So it could be used for many sonar applications, right? For search, yes, absolutely, absolutely, submarines, right? And you see, we are not restricted by only sound. We just need to take the information in IR or in UV or and just convert it into electrical signal, and then this architecture has to be used. Make sense? So that's what is about the barn owl. Okay. We go to the next lecture. Any question on this one? Okay, so we can do the locust. Locust, you guys want to do the collision avoidance, or should we go to multisensory integration? Locust I have discussed, huh? Yeah. Cycling. That's fine. That in the TEDx talk, this was locust. Yeah. I think let's go to multisensory integration. Okay. Yes. Correct. This is no recombination. So this is just the electric field. Yeah. Yeah. Well, it depends on what exact modeling we are talking about. We can talk about the modeling part, in more details later, But I think this is a way simpler modeling. You just create the geometry and you just want to look at the field distribution. This will probably not require you to look into any recombination model or anything. Never. First is experiments, then comes simulation. Yeah, yeah. Okay. Very rarely we, first do simulation and then go ahead and make devices. Never. We go ahead and make devices. If it doesn't work, we forget about it. If it works, we make it better. And then if required, let's say the reviewers ask, okay, can you do some modeling? Then we do the modeling. Because experiments is the ultimate truth, right? So, okay. So let's now look into multisensory integration. It's kind of inspired by octopus. And the reason for that is, octopus is one of the most intelligent underwater aquatic, species. It navigates with two information. One is the tactile information. Its entire body is actually touch sensors. Like the catfish's entire body is, tongue. Its entire body is actually, it has actually distributed intelligence. So generally, in human, the intelligence is all in the brain. But in case of octopus, the intelligence is everywhere. Okay, even every arm of an octopus is a brain. Okay, so it's a very unique species, and it navigates in underwater environment with the help of both the tactile information that it gets from its tentacles, and it has a polarized vision as well. Okay, so it is very good in detecting light, even in a very dark environment. Small amount of light it can detect. But anyways, we derive the inspiration from there, but we show the importance of multisensory integration. And let me first define what does multisensory integration means, because today we are in this era of Internet of Things, right, which is literally, all the sensors which are distributed around us, and then, all the sensors are sending some information to a processing unit, central processing unit, right, and then processing unit kind of makes some decision about, whether to light on the room, or, whether, what is the weather outside, whether you want to have some coffee, right. So, or let's say, for example, when you're driving a car, all the autonomous cars, right, they're getting a lot of information through optical sensors, acoustic sensors, right, and then they're deciding whether to, speed, whether to brake, right. So this is what is happening, right. This is called the sensor fusion technology, right. So you're not only relying on one sensor, but many sensors and fusing it together using a central processor, right. And if you think about us, right, we are also something like that, because we gather information not only from our eyes when we are watching a, let's say, movie. We are not only, looking at the visual scene, but, we are probably also looking into, the ambience, where we are sitting. So every information impacts our decision making, whether we like something or we do not like something, right. But in this sensor fusion technology, the sensors talk to each other. Okay, they never talk among themselves. They always talk to a central processor. Okay, this thing has not started yet. This is we call the cross-sensor modulation. This is something that happens in our body all the time, and that's why when you have information from one sensor to the other, you can only add them up, and 1 plus 1 can only be 2 or less than 2 based on how much information you are losing while transmitting this thing, right? But in nature, that is actually not true. Okay, 1 plus 1 can actually be much greater than 2 in certain instances. That's what I'm going to tell you. So integration is what? Addition, right? And never can we add two things to become more than either one, right? I mean, so what we will show you is that the response, this is called super additivity. This is a feature of multisensory integration. Let's say your visual gives you this much response, and tactile gives you this much response. If you add these two, you should probably get somewhere up to this. But actually, it goes up, almost, exponentially. Okay, this is what we call super additivity. That's a feature of multisensory integration, and we'll see that. Okay, so where is multisensory integration useful? That's the question we need to ask. Why in nature this exists? Why does it help? Okay, so here, let's say, for example, if I show you this picture. Okay, so let's say I ask you to enter a room, and that's, let's say, an auditorium. It's initially completely dark. But if you enter that room and if you have no information about whether it's an auditorium or not, how will you navigate? Right? No, you can by touching. Right? Because it is completely dark. So you will use your tactile information to see, oh, if there is something in front of me, whether I'm going to topple or not. Right? By touching. Correct? But if for a very short period of time, if I show you this, like light comes and goes, right? Will it make your life easier in navigating now? Correct? So a small spark of that information, which is a visual information because you see something, now even if the room is dark, you can navigate better. Correct? So what happened? What happened here is, if it was a typical robot which does not remember anything, it will have the same difficulty in navigating whether there was a light spark or not. But in our case, it is not the case because we have a visual memory, and now it is easier for us to navigate. You see this part aspect? This is multisensory integration because this has a lot of these benefits, and this is what I am going to show you. The other important thing is inverse effectiveness effect. What does it mean? That let's say if the light is completely on, right? Will you take help of your tactile sensation to navigate anymore? No. You can properly see, you will just simply straight walk and go and sit on a chair, right? So it is important when one of the information is very weak. Correct? And that is the case we mostly care about. Let's say, for example, if you're walking in a forest, right? If you're walking in a forest in a complete, during the night time, you will be extremely cautious about the sound information, right? Because you don't know whether there is a, some tiger, snake, or whatever is there. So you'll be very cautious, right? Because your optical information is not there. But if you're walking in the daytime, you are not that afraid, or not putting a lot of importance on your hearing capability, right? But if you are walking in the complete darkness, you are focusing both your eyes as well as your ears are putting effort in order to make the information amplify so that you are not losing your life, right? It's an evolutionary process that gives these two properties, super additivity, but super additivity only when the cues are weak. When the cues are strong, I don't need to add them. Correct? That's why the effectiveness goes down as the strength of an individual cue becomes strong. Because then that removes resources that your body needs to spend. If you need to spend resources both on eyes, both on ears, energy is being consumed, right? So this is another feature of multisensory integration. Yes, now we are going to look into this multisensory integration, how to achieve that using our devices, right? So we are using, again, our favorite MOS2 transistor. We have already shown monolayer MOS2 is a good photodetector, but now it is not good for touch sensation. Okay, so I have to bring in something else. And the something else is what we call a triboelectric nanogenerator. Okay, this is an entire field in itself. This is nothing. So if you create, this kind of a structure, Captain aluminum and air, you see it's a metal, and there's a lot of charges over this surface. So when you touch, these charges actually pass, when you touch it physically, and that actually creates a voltage. So by touching, you can generate voltage. That's why it is called a triboelectric nanogenerator. The voltages that are generated are actually nanovolts, very small voltages are generated. But this is another way of energy conversion. This is actually an energy conversion device, right? You're converting touch energy into electrical spikes, right? That's what your body is also doing, your skin is doing. Your touch sensation gets converted into this thing. And then you see that I have created these 3 different types of, by which I am touching, because the strength of the touch is important, right? If I touch it, gently versus if I touch it very strongly, is going to make a difference. Let's say, for example, you are in dark and you are inside a museum, right? Now you want to navigate in dark. Will you do something like this, or will you be very careful? Very careful, right? You will be doing a very soft touch. But if you do a soft touch, the information that you get back is also very minuscule, right? So we have to also, that's what I'm saying, when the cues are very weak and you are trying to navigate, how do you do it, right? How do you navigate in a museum in dark condition, right? And this is going to be very important mostly for army application, because you're already thinking, why do I care about moving in a museum at dark? I mean, I'm not that English movie where, someone was stuck in this museum for a night, right? What was that movie? Night at the Museum, right? This is very good for the army because, I mean, there might be mines and everything and you're trying to navigate in a forest, you do not know whether there are terrorists or anything, right? So you have to be extremely careful about what you touch, right? Something blows out, then you're done, right? That's why it is important. This is just a, demonstration to use for those applications, then deriving inspiration from nature. So now let's see what happens with just the tactile response. So you see, whenever I touch it, right, I will create a voltage, and this voltage is kind of connected to the back gate of the transistor. So what I will do is I will get the spikes. Right? Every time I touch, I will get a spike because this will generate a voltage that is applied to my gate that will allow my current to flow. So I get a spike. Right? And based on how strong the touch is, I get higher magnitude of spikes. So that is literally converting the touch information into current. Right? And the strength of the touch is kind of characterized by the amount of current that I'm getting. Clear? Right? So now the next thing is, instead of having a single touch, if I want to add two touch, it should be additive. So 1 plus 1 should be kind of 2, right? And that's what we show. So instead of T1, if I have T1 plus T1 both at the same time, it adds up, right? So if I now simply wanted to plot, this is called the unisensory integration. So compared to 1 touch, the 2 touch is just double the strength. Expected, no problem, right? So unisensory integration does not have this super additive property. That's what I'm trying to get. It's just additive. Okay, no problem. But we can make our device a touch sensor, okay, by integrating it with this triboelectric nanogenerator. Now let's look into light. Right? If I have light in dark, there is no response, and then as I increase the illumination time, right? For example, if I show the room for a shorter time versus a longer time, so response will be better, right? Because you have seen it for longer. So that's what is happening, right? So visual cues, as it increases, and he said the cues are characterized by the duration, my light, the current increases. Okay? And I can do the same thing, right? I can do once or twice, right? And it is also kind of additive in nature. You can see the double is actually twice the single. Right? So again, I did not achieve any super additivity just by adding the same cue. And it should not be the case, right? I mean, if I'm adding the same cue. But now what happens if I do that both at the same time? While I'm touching, I'm also putting a little bit of light, right? That will be multisensory integration because both sensor information are now coming together, right? And then if I do that, okay, this is a plot. I kind of design a quantity. So you can see this plot. These plots don't tell you much. So what I'm showing you over here is that the visual intensity is increasing and the tactile intensity is also increasing. So I see an increasing trend, no problem. But then I define a quantity which is this multisensory integration factor. What is the visuo-tactile response? That means both the senses are there, and divided by what is the response when only one of them is present, right? And that ratio will tell me if it is greater than 2, then I have achieved super additivity. Electrical response. This is the electrical response, the current response, right? Is when both are present. Only visual plus only tactile. That's separate. That's what your current sensors do. Visual comes, tactile comes, it adds. But now we are adding those two things because this is interacting using a single device. Because the tactile response and the visual response are acting on the same MOS transistor, right? And if I do that, then you see that when look at the numbers, the addition becomes 30 times more than just adding them together, right? And that is something we could do because of this nonlinear characteristics of the MOS2 transistor, and we are operating it in the subthreshold. So whenever there is a touch, there is an exponential change in the response, right? And you see, more important thing is that T1 is a weak signal and V1 is a weak signal. And for them, the integration factor is the highest, which means when the cues are weak, my multisensory integration is best. And when I have T4 and V3, there's a very big touch and a very big visual cue, no multisensory integration because I don't need it, right? So this is the inverse effectiveness effect. Remember two criteria, super additivity and inverse effectiveness effect. And this is going to be extremely transformative when you combine sensors together. Make sense, right? Because you don't care when the cues are the information is very strong. You can make decision based on either the light information or the tactile information. When both are very strong, weak, if you just add them, you still don't get it unless you amplify it in such a manner, right, that it becomes detectable. So this is a very different principle compared to the sensor fusion technology that we use today. And it can only be done if we start the integration at the device level. You see, because we did not we did not use a photodetector and a tactile sensor separately. We combined it, we fused it, right? This is the ultimate sensor fusion that you can do, and that's what the biology does all the time. Right? So that's what this thing is. And then you can actually, this is, I'm going to go very quickly. This is actually a crayfish. This combines three information. Okay, it combines tactile, visual, and chemical. Okay. I will probably remove, will not go into detail of that. Here actually you have this tactile neuron being controlled by both the visual neuron and the chemical neuron. So even better in terms of integration, because three senses are coming together, and you can achieve the same thing, the superadditivity, in a system like that. This is a separate paper. You can read it, and the inverse effectiveness effect. So here we have combined three. You have seen this picture earlier today. This is a graphene chemisensor. This is a triboelectric nanogenerator, and this is a MOS2 photodetector. So now fuse these three things together. Okay. I will just show you the circuit, because here what we are doing is, here is the photodetector. In the previous example, we just added the tactile sensor to the gate, right? Now we are applying this graphene chemisensor information, converting it into some voltages, and also applying that to the gate. Okay, this is a little bit more involved circuit. We don't need to go into the details of this. So if you are interested, I can talk to you about that later. Okay, but you see, when you fuse things, it has to be at the very device level. It cannot be separate. Okay, that's the the take-home message from this slide. Okay, this is our setup. So don't worry about that. You can see you have the light, you have the chemical, you have the touch, everything, and then you fuse it together for the sensor fusion technology. I think I will just skip this. Okay, this I will come back to later when we talk about maybe the multisensory thing. So the same effect is seen actually. Okay, so I'll just skip these slides for the time being. And this is what I'm going to show you here. You see that I was talking about again this. Let's say you have a surge vehicle underwater, right? You see the detection limit becomes way further when you combine tactile, chemical, and visual information. That's what the crayfish also does. If you have any one of this, you never achieve such a huge radius of detection. It simply makes your detection much easier when you combine the cues together. Okay, so that's what I'm kind of alluding to over here. Okay? Easier. Detection becomes easier. Okay, because you're combining multiple information, right? Because if you have a ship wreckage or something you're trying to find, there might be some oil spill. That's a chemical information. Right? There might be more fishes around. That will give you more tactile information because the water will be more turbulent over there. Right? And then if there is some flashes of light in a surge vehicle, you can also maybe see something. But if it's only one of this, it becomes more difficult to search. See? So that is a key idea, right? It will become more effective, right? And then I think these are the the summary. That's the key parameter. That's the key parameter. What is the integration improvement that I am getting versus all working together? That's the ratio. It could be like 30 times. 30 times. Right? That's quite a big improvement in terms of this. Right? So this is what we showed, light to electrical, because that's what the brain is. Right? Everything is converted into electrical signal, and then you combine. Right? Using specific circuits. So here there's a lot of circuits involved as well. We did not talk about circuits, but you design those specific circuits to perform this, more complex task. But these two papers, if you read, both published very recently. One was in Nature Com and the other one was in Nanolatest. You should get a full picture of, this multisensory integration. Good? Okay. What is next? What do you guys want to know next? Let me see. Yes. Yeah, tell me. Yeah, exactly. 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 Yes. Happens all the time in biology because biology is very adaptable. It kind of retrains things. Neurons can make new connections, which is not possible with solid state devices. Okay. The next topic that we might be able to do is, let's see, we can cover. So how much time do we have? 25 minutes we have, right? Okay, so if we have 25 minutes, I could do this one. It's a little bit different topic, related to neuromorphic though, but emotional intelligence. That is something we can talk about. Okay. It's just not artificial intelligence. We are now getting into a very debated domain of emotional intelligence. If we are not already happy with our machines being artificial intelligence, giving emotions to them. Okay. Just 2 minutes. I will start. Okay, so this is again, as I was mentioning yesterday, we are trying to design a bio-inspired gustatory circuit, okay, for mimicking both the psychology and the physiology of feeding behavior, okay, because as we were talking about, sensor fusion and better decision making, right? So machines always makes decision based on logic, right? But we human beings don't always make decision based on logic. Emotion is equally involved in our decision making process, for which sometimes we make the good decision, right decision, sometimes we take terrible decisions, right? So if you really wanted to think about an artificial general intelligence, right, you'll probably wanted to integrate emotional intelligence to that as well. Where it will lead to, I don't know. Okay, don't ask me that. I hope that I will not survive to the date that the artificial intelligence becomes so emotional, or it might be a good thing, right? So we do not know. As I'm saying, we do not know whether it's going to be good or bad. But I mean, scientific discoveries are never driven by whether it's going to enable something good or bad. You just do it. I mean, the atom bomb was not made to be dropped on the Hiroshima or Nagasaki, right? So Okay. So I think let's see, how we can design that. The reason for that is, I mean, this is the current day robots, right? I mean, that kind of makes the decision based on logic, but the technology tomorrow should probably look like this. Okay. Uh, and the main reason for that is what distinguishes the artificial intelligence from the natural intelligence is that we have two parts of the brain, right? We have one of the hemisphere which generally takes logical decisions, right? But then the other part of the brain is actually very colorful. Okay, it doesn't take decision based on logic, right? That is where all the is there. But if you think about chemically, the two parts of the brain are exactly similar. The same neurons, the same synapses, right? It is not that there are separate types of chemicals on two parts of the brain. It's even the same neurotransmitters, dopamine, serotonin. So they're not different, right? But yet, the whatever information we get in, it goes to both parts of the brain, right? Because that's how the final decision is made, right? And one part of the brain is purely, the physiology, correct? The other part is mostly to deal with psychology, right? And this field of psychology will actually have a lot of importance going forward. And this is actually also related to a lot of human health, right? And I mean, this part of the brain has been mimicked by this artificial neural network, but there is really nothing mimicking the psychological part, correct? And that's what we are trying to kind of match. Now let's take the example of feeding, because I mean, this is a huge space. When we talk about decision making, in what context are we talking about, right? So let's take a very simple example, because we need to understand the brain circuits which are responsible for our emotion, or can we represent emotion with some neural circuits, because at the end of the day the brain is only electrical spikes, right? So now let's think about feeding. When do we feed? When do we feed? We feed when we are hungry, right? So hunger can be a state variable. Let's say it's H. So whenever my hunger is high, I will feed. But I will also feed when I have some appetite or liking, right? For example, if I give you a rasgulla at the end of your food, you might be full with having the biryani, right? But even after that, if I give you a brownie or a cheesecake, थोड़ा खा लेते हैं, हाँ? That you are eating not because you are hungry, that is because you like it, right? After biryani, if I give you a Kerala, will you eat? No, right? But then let's say if you are completely hungry, biryani नहीं है, सिर्फ करेला ही है, you will eat, right? So therefore, there are two things, and this appetite is really your psychology, right? So that determines feeding. So if I now want to build a circuit that takes into account both the emotional and the logical aspect of the brain, what will be the truth table? Because that's how we make circuits, right? We have to make a truth table, right? This is just an example with this broccoli and pizza. My student liked it, and that I told you that he was presenting in a comprehensive exam, and this professor was a little bit fat. He could not go, and there was pizza being served in that comprehensive exam. He could not go and take the pizza after seeing this. Okay, so and then we feed, right? So feed is the output variable. The input is the physiological state and the psychological state, and the decision is whether I want to feed or not. Right? So we have to put it in a mathematical format. Otherwise, I cannot design the the solid state circuits. Right? So now let's see what will be the truth table. Right? If hunger is 1, that means I'm hungry. I don't care about my liking or disliking. I'm simply going to eat it. That means I'm going to feed. Right? But if I am not hungry, then I will only eat if I like it. Right? So this is the truth table, because that's the first step of designing a circuit. You make the truth table. That's the don't care condition. Reminds you something, people who have taken circuit theory courses, right? That's the don't care condition. So what will be, therefore, my logic expression for this? Simple. H plus H bar A. Right? Then I am literally done actually. Right? I have captured both the emotion and the physiological aspect of the brain. Now I have to go and simply make it. Right? The making part is easy. How to implement this mechanism in hardware, right? So first of all, we need a tongue. We talked about tongue today in the morning, right? The tongue we already have with graphene, right? And the other thing is that we need is, it is only tongue, right? This is only taste, correct? There is nothing else is involved. But now there should be two pathways. The tongue should send the information through this hunger neuron to this physiological part, and through this appetite neuron through the emotional side of the brain, right? So therefore, I will show you how we are making this electronic tongue a little bit different, because right now it's not food sensing but also decision making. So I have to use two kind of sensors, and then I need to kind of convert it using this appetite neuron, and the hunger neuron, and put it to the gustatory cortex where this circuit exists. This is the circuit that implements this operation, H plus H bar A. That's really the connection between your emotional side and the physiological side. You see, that's what I have to do. So this is a NOT gate, right? This is AND gate, and this is an OR gate, right? You see, the last operation is OR, correct? So this is where the H comes, the hunger neuron information comes straight, and then this is H bar, and then here it is your A. That A comes from this neuron, and then they make the decision. Correct? Okay. Rest is very easy. The memory register is used. I will come to that. I will come to that because it is programmable. Because appetite is something that also depends upon your mood, right? And that you need to program, right? If you're in a good mood, you will probably eat that cheesecake. If you are not in a good mood, then leke jao bhai, abhi khana nahi hai. Huh? Yes.
So actually, hunger intake and appetite, this should be analog, right? Because there is an extent also.
Huh?
It's not like that.
There's a lot, right? I'm saying that this is the very first demonstration of integrating emotional intelligence, and you can build from that. You see, I mean, you can bring in a lot of other aspects as well, right? Yeah. I mean, you can, the more complex you make that circuit, that's why we human beings are so complex, right? I mean, I know that you like a cheesecake, I bring it for you, right, take it away. Because today you are in a different mood, maybe something else has happened to you, right? So this circuit, if I can use another input, right, which could be your mood, correct? So I could simply add more and more, but I have to start building these neural circuits to bring both the psychological and physiological aspects. That's what I'm trying to show over here with a very simple example, right? And so then we use graphene, this have seen again, right? But now this graphene chemitransistor is another chip, okay? We don't care about, so this is all the details, different chip altogether. This is a graphene chemisensor response that we have already seen on the liquid on top. These all have been discussed, so which makes my life easier now, right? So you all know about this, how a graphene tongue works. So I simply gathered that information. But you see, this information is in current domain. But logic circuits only work with voltages, right? So what I have to do is I have to, take two graphene devices. Okay, these are for different, coffee, tea. It's just different responses. I use two graphene devices and connect them together. And in the middle node, I will get a voltage. Okay. Now here also, this device-to-device variation is very important, because if the two devices are exactly the same, and if I put a solution over there, right, will it matter what solution I put on this intermediate voltage? Tell me this thing, right? So this is a graphene chemitransistor. This is another graphene chemitransistor. There is a voltage applied over here, voltage applied over here. What will be my VC? Tell me first, what will be my VC? Is there a mathematical expression for VC? This is not a NOT gate. This is just a voltage divider.
Okay. Looking very identical like inverter.
Yeah, but this has to be a P and this has to be an N in order for it to be an inverter. This is just a voltage divider. There is a gate. Even if it is not there, this is a resistor. This is another resistor, and there is a node over here. What will be the voltage over here? This will be VDD times, R1 divided by R1 plus R2. Right, that's what it is, correct? Now, if I put solution A versus solution B, will this voltage change, is what I'm asking. Because it's the ratio of the two resistances, it will not. If the two graphene devices are identical. If two are exactly the same, right? So here also device to device variation comes to a rescue, because since the two devices are different, right, then it will give you a very non-monotonic dependence of the VC with the gate voltage. Okay? If you do the math, you will find that, you know, the neuron looks like this, and if you have a different solution like sugar versus bitter, you see that the response is different. So far so good, right? But this voltage information is because we have to use logic circuits. These are analog values. I have to convert this analog voltage into digital one, because the circuit that we did is a digital circuit. I need ones and zeros for that, correct? So I take this analog information, right, and you can see that for different sweet, the hunger neuron, as the solution concentration changes, you know, this is the response of the device, and I can threshold it. Okay, and the thresholding part, let me just see. Okay, is hunger and this is satisfied, because I'm also bringing in one more aspect. You know, how long you will feed will depend upon how long you are hungry, right? So once you have the food, as the food you getting consumed, you know, the device response keeps changing, and after some time, you see that the response kind of goes from one state to the other. That time you are actually satisfied. You will stop feeding at that point of time, right? And I can actually do that even with the device, and you can see if it's a sweet substance, it feeds for longer. If it's a bitter substance, it feeds for shorter period of time, because your hunger generally gets satisfied earlier if you're eating Karela sabji versus biryani, right? So that kind of is also captured in this device. Okay, and the same is for the appetite actually, right? So after some time you don't have appetite. If I keep feeding you cheesecake after cheesecake, I will get you know, very bored about eating more cheesecake, right? But I have known, you know, during our father's generation, one person can use 40 rasgullas, 50 rasgullas. I cannot eat more than 2, then I will saturate, right? That's like appetite versus apathy. Like, even if this is something you like, but after some time you will not like it anymore, right? So that is also kind of captured, okay, with this thing. And bitter is something for which you don't even have appetite. It's always apathy, right? But for sweet, you have an appetite up to some time, and then you don't like it, right? So this is also kind of captured using this device. So now, once this is done, then we digitize this hunger and appetite neuron. And these are the circuits for analog to digital conversion. Okay, this is nothing but literally a comparator circuit. A comparator circuit simply compares with a given threshold. And you see this circuit has an output input characteristics like this. So anything below this point, it will be 0. Anything above this, it goes to 2. So that's like, you know, logic 0 and logic 1. Okay, that's what we do. So we take that analog signal and convert it into digital spikes, right? The same thing, and this is a lot of details of the circuit. You know, this is actually made using MOS2 devices. Okay, and you can see that we are using a 4-stage cascaded inverter. This is actually an inverter circuit, and we cascade 4 stages, because if you use 2-stage, you see then it is like a not like a very abrupt response, right? As you go to more and more stages, the gain of the inverter increases, and you become like a very sharp transition. Got this part, right? So this is a comparator that we built. Okay, so therefore, you know, all this information which were, you know, kind of in the analog domain, because they're continuously changing and they are in the range of, you know, 0.1 to 0.3, now get converted into digital signals, right? And once we have the digital signals, right, then it's very easy. Then you make these circuits. These are also possible to make AND gate, OR gate, logic gates, right? You put the information in there. So now you have sweet and bitter, right? And then this is your H bar. This is your A. This is your H bar A, and this is your feeding. You can see that if it is sweet, you feed for longer. If it is bitter, you feed for kind of lesser, right? So that was our ultimate objective, is to bring in, and this involves, you know, both the emotional and the physiological factor, right? And then, you know, this is also, we are using an MEM transistor, the question that you asked, because using the MEM transistor, I can change this comparator voltage. If somebody has sugar, then they will probably only eat one cheesecake and then they will stop. Correct? So that can also be programmed. So for each individual, you can program what is the threshold of their hunger. And even some people have more, hunger, and some people have less hunger. That results in whether you are this or this. No, right? So that can be captured using these, programmable devices. That's why we are using this programmable MEM transistors for this. And I think programmability I have already explained, right? This was from previous lectures, right? We have already talked about that. And the potential application of gustatory circuit, right? This guy keeps feeding for long, right? Sweet leads to diabetic, right? And you can show that, you just that how long you feed can also be programmed. The longer you feed, more you become like that person. Okay. So the conclusion is that, so this is the first time we have been able to develop a circuit which takes into account the emotional aspect, and then we are trying to kind of combine this graphene chemisensor and MOS2 based. So our gustatory cortex is now also made out of MOS2 devices, and then the tongue is graphene. So tongue is graphene and gustatory cortex is MOS2 transistor, and this is that demonstration. Okay, very simple, but a little bit going into a different trajectory compared to the typical neuromorphic computing devices. Okay, any questions on this? These are short lectures.
During runtime, how can we program the transistor maintenance?
Not during runtime. You can program it before or after, right? You can set the state of the device. It's almost like before you go for eating, you know what your mood is, so that will determine how much you are going to eat, right? So that's what I mean. Where is the application of this? Many places, right? I mean, if you think about the next generation of restaurants, they're probably going to use this kind of tricks, right? If they know what you like, they will probably make sure that the smell of the food that you get, the texture of the food that you get is according to your liking. This is already happening actually. A lot of advertisement, I mean, in fact, McDonald's have started doing that. This is something called some neuro advertisement or something. They know what kind of smell will bring you inside the shop, and they will ensure that the fries they are cooking actually gives out that kind of a smell. Okay, so they are playing with your emotion, and you, without knowing, right, you are getting dragged towards, because they have all the information. What kind of food you search for, what did you like to do, what are you eating, all information is there for Google. So they just have to learn their machine learning model. In fact, I feel like today Google knows about us more than even we know ourselves. So they can even start playing with your subconscious, and this is like making their life easier. So, but I can't help. Okay, thank you.